Perfect. So remember what we have done in the last class. We went through fluids, right? We went through fluids. We went through the differences between solids, liquids, and gases. And in terms of atomic levels, atomic positions, and stuff like that, and also macroscopically and microscopically both, we have compared solids, liquids, and gases. And we went through then density. Density is defined as mass per unit volume. Gram per centimeter cube is a unit that can be used. Kilogram per meter cubed can be used. You can also use pounds per square, feet. Cubic feet. That also is fine. But the SI unit is only one, which is kilogram per meter cubed. And we also went through the density of water as 1 gram per cubic centimeter. So if I take 1 centimeter cube of water, or 1 ml of water, which is basically the same thing, it will weigh 1 gram. So 500 ml, a water bottle of 500 ml will weigh 500 grams. In terms of SI units, 1 meter cubed will be the volume, and it will be 1,000 kilograms the mass. So the density of water in SI units will be 1,000 kilogram per meter cubed, which is the same as 1 gram per centimeter cube. Okay? And then we compared some of the densities of different substances just for comparison's sake. Aluminum is 2.7, iron is 7.8, is heavier. Ice is only 0.9, and copper is 9, it's heavy. Lead is more heavy. Mercury is very heavy, 13.6 gram per centimeter cube. Gold is 19.2 gram per centimeter cube. Oil is 0.8. So it's because oil floats on water, so definitely it is less than 1. Is that clear? And wood can be anywhere between 0.1 to 0.7 or 0.2 to 0.7. It depends on the type of wood. Air is very light, 0.0013 gram per centimeter cube. In kilogram per meter cubed is 1.3 kilogram per meter cubed. And we did a little experiment over here to find the mass of air in this room. So we measured the room dimensions as 9.70 meters as length, and then 2.80 meters is the height, and 6.50 meters is the width of the room. So we found out that the total volume was 177 centimeter cubed, and using the density value as 1.3 kilogram per meter cubed, we could measure the mass, or we could calculate the mass by using the formula, and we got the answer as 230 kilograms. We can use that formula using the triangle or just use the basic formula. Here are some other examples. If the volume of water is 250 ml, which is 250 centimeter cubed, and mass of water is what? So we did that. And I gave you other examples to find out how the density equation is used. Any questions on things so far? People at home? Any questions? Respond.
No, sir.
No questions. Okay.
No, sir.
Good. Thank you. So let's move on to the next aspect of this chapter, and it's called pressure. So write down notes. Pressure. It seems like, it's almost the same as force. Apply a pressure, apply a force. Seems like it's the same thing, but there is a big difference. There's a big difference. Pressure and force are totally different things. So what can damage a surface or an object? What can damage something is actually pressure, not the force. You can apply a huge force on an object, but it's probably not going to do any damage. Like for example, on this table, I can use my hands and just like, I can hit the table, right? Anything happen to the table? Nothing. Whereas if I take a sharp knife and just drop it on the table like this, I'm not offering too much force on the table, but will the table get damaged? So it is not the force that matters, it is the pressure, which is basically the concentration of force. Get it? It's a concentration of force, like how much is a force per unit area. That is called pressure. So what is the definition of pressure? It is a force per unit area. It's a force per unit area. So pressure is F over A. That's our basic equation for pressure. Capital P stands for pressure. Now, we also use capital P for power. Remember, when we did mechanics and all that, we used capital P for power. That's fine. We can use it at different places. We're using the same letters. But here in this chapter, capital P will stand for pressure. And so what's pressure? It is a force per unit area. So it is not the force that matters, it's the pressure that matters. Let's say, for example, you laid new hardwood floor in your home and a couple of people are trying to come and look at the product. And one of them is a huge 300-pound person. And he comes and stomps with his huge feet on the hardwood floor. Anything happens to the hardwood floor? Probably nothing, right? And then comes a little girl with high heel shoes tiptoeing across your hardwood floor. Will you be concerned? You will be concerned. Not because she's heavy, but because of the high heel, she can apply more pressure on the surface, and that will do the damage. So what can do the damage is not the force, but the pressure created. You may get hit by a volleyball. You may get hit by a volleyball very fast and nothing will happen to you. Whereas a small marble or a small stone coming and hitting you will cause damage, right? It will cause damage. So that's where we are actually looking at the pressure. So pressure is what causes damage, not the force. Now when you use a thumbtack, you know what a thumbtack is, right? Right? If you want to put the thumbtack on a bulletin board, you're going to use your thumb over here. Looks like a thumb, okay. You're going to use a thumb over here and push the pin, right? Now tell me, on which side is the force bigger? On the thumb side or on the pin side? Be careful when you answer this. Which side is the force bigger? On the thumb side or on the pin side?
Aren't they the same?
It is the same. Force is the same. Because, you're pushing from here and the force gets transferred to the other side, right? But which side experiences more pressure? Will your thumb experience more pressure or the pin experience more pressure? Or the board experience more pressure? The pin. That's because the same force is applied on a small point. So the area is very tiny. When you look at a pin, the area is very tiny. And that is what causes the damage. So therefore the pin pierces the board, but nothing happens to your thumb. Your thumb is fine. Get it? The force is the same, but the pressure is more on the pin side. The same with a knife. A sharp knife versus a blunt knife. You are applying the same force. But then the sharp knife cuts through very easily. The blunt knife is not cutting well. That's because what does the cutting is the pressure and not the force. Make sense? Okay. So let's look at the units of pressure. Unit of pressure. Pressure is force upon area. Now what is the unit of force? Newton. And what's the unit of area? Right, Aiden? What's the unit of area? Area of something. Meter times meter. Meter square. Got it? Just think about it always. Meter times meter. Meter square. That's area. So Newton per meter square. That is the SI unit. SI unit of pressure. The SI unit of pressure is newtons per meter square, also called Pascal, PA. Pascal is a shortcut unit for pressure, SI unit. So SI unit for pressure is Pascal, or Newton per meter square if you want to split it up. Any questions so far? Good. Now what are other units? How much pressure do you put into your tires? PSI. Other units of pressure? PSI. What's PSI standing for?
Pounds per square inch.
Pounds per inch square. See, it's like Newton per meter square. You can see the connection, right? It's pounds per inch square. Or you can have lbs per feet square. That's also fine. Pounds per square feet. They're all units of pressure. But what is the SI unit of pressure? Only one. The SI unit of pressure is Pascal or Newton per meter square. You can always use other units for convenience, but it is definitely not going to go into equations. Got it? So when you are putting pressure into your tires, you can always say, you know, oh, I put 35 psi, I put 40 psi and all that stuff. That's fine. As long as you only mention it to somebody and that's it, end of the deal. But if you're going to substitute into equations, we have to put it down properly. Is that clear, everybody? Good. No questions at all so far? You have a quiz coming up on this, so you better ask questions if you have any questions. Okay. So pressure, the unit is Pascal. Definition is force per unit area. And let's see some examples. Let's look at an example. Let's say I've got a box that has a mass of 50 kilograms. The mass of the box is 50 kilograms and it is resting on a table. The box is resting on a table. What is the pressure the box is applying on the table? What's the pressure that the box is applying on the table? So what's the pressure, P? So what do you need for pressure? What are the two things you need for pressure? Yeah, the newtons, the weight, newtons, and area. So you need the force and area. You need the force and area. So how much force is this table, is the box applying on the table? How much force is offered on the table? What do you call that force? What is the force offered by the box on the table? What force is that? Gravitational force, which is the weight. You can't use 50 for force. You need to find out how much force that 50 kilogram is going to offer. So weight is equal to mass times gravity. So mass is 50 and gravity is 9.8. And so it is 490 newtons. So we got the Newton part of it. So pressure is 490 on the top over area. I've not given you the area. So let me give you the area now. The area of the box. Let's say the area is 0.25 meters squared. If the area is 0.25 meters square, now you can just put in 0.25 meters square. So newtons meter square. Tell me what the answer is. That will tell you the pressure.
31.
How much?
31 newtons per meter squared.
Are you sure?
Yeah.
490 divided by 0.25. Yeah, you'll get 1,960. What did you do? Check your calculations. 490 divided by 0.25 is 1,960. What's the unit? Newton per meter square, or what's Pascal? Pascal. P-A-S-C-A-L. You just write P-A. Just like Newton is for, N is for Newton, P-A is for Pascal. Okay. So you can have a shortcut unit, or you can write Newton per meter square. Both are right. No. Then it'll get confused with the pressure. Yeah, I mean, like you can't say P is equal to 1960P, it makes no sense. Yeah, that's why we write PA, because then we know that it is Pascal. So it's universally accepted unit, PA. Okay. All right, so you understand how to find the pressure. If you're given the force, you're given the area, you can find the pressure. Now, if the force is given to you, in Newton straight away, then you don't have to multiply by 9.8. You have to multiply by 9.8 only if you want to find the weight. Like if I say you are sitting on the chair, right? You and the chair together, is it applying of pressure on the floor? Yes? How do you find that out? Calculate the total weight of you and the chair together, and then look at the area of the shoes, the 4 shoes. If you can find out the area of the 4 shoes, then that is our area, then divide it. Now what if the area is smaller than this? Then the pressure will be too much, right? The floor will get damaged. Some people put tennis ball and all that under the under the chairs. Have you seen it? It's because, like less pressure, less damage to the floor. Now, sometimes when the shoes are missing, it can actually cause dents on the floor. If you're going to use it on a hardwood floor, imagine there's no shoe, it is going to damage the hardwood floor. Because of the pressure, not because of the force. It's the same force. When you're sitting, the same force. I've seen an elephant put its leg on a man's body, put one step, and then take another step. I've seen that happen. What they do is they put a plank of wood on him. Yeah, exactly. So you put a plank of wood on the body of the person, and the elephant is putting his feet on the plank, and then he's fine underneath because it's distributing the weight. Otherwise, what will happen is, if the feet is resting on his ribs, that's finished. Right? Yeah, so understand the concept of pressure itself. You understand pressure clearly? This is what pressure, this is how you find pressure created by a solid. Now let's find out about a liquid. How is the pressure offered by a liquid? So pressure by liquid. So let's look at a beaker of water or liquid. So we got some water here. Will the water exert a pressure at the bottom of the beaker? Yes? No? Will the water inside the beaker apply a pressure at the bottom of the beaker? Yes. Just like the previous case. If that weight was sitting on the table and pushing the table and creating a pressure, this also will do the same thing. So there will definitely be a pressure offered right here. The pressure will be offered there. And what is that pressure equal to? Force over area. Now we got to think about a couple of things. Force. What is force? It's a weight of the water, correct? So force is the weight of the water, which is mg. And area is A. Now what is weight? Is mg. Now what is mass? Now the density of this liquid, I don't have to say it's water, it can be anything. The density is given by a symbol called rho. Now I've not used the density symbol as rho when I taught you densities. Let me write that also down. See, I wrote density as D maybe. Right? I wrote D as the density, which is not always the symbol that is used. The actual symbol that is used for density is rho. It's a Greek letter. Because capital D can be confused with diameter. We can always be confused with that. So that's why rho is mass over volume. That is the equation. So what is rho? It's a Greek letter. See how it's written down? Just start writing an E and then pull it down. It is a symbol. It sounds like rho, R-O-W. And it's a Greek letter. It's a Greek R. So rho is a symbol that we are going to use. In fact, your textbook also uses rho as a symbol for density. So although I said D as density, understand that rho is a very common symbol that is used. So I'm coming back here again. So rho is the density. the height of this fluid. How much height is there? That is h. The area is a. The area of the base, the area of the bottom. The area of the bottom is a. Because that whole water is sitting on the bottom area. That's why. You got it? So only we need the contact area, like how much is sitting. Okay, so now what is the density equation? Density is equal to mass over volume, correct? All right, so what is mass? Mass is density times volume. Is that right so far? Is everyone okay at home?
Yes.
Good, thank you. So mass is density times volume. Now look at this volume and tell me how much is the volume of water in this, or liquid? How much is the volume of the liquid in that beaker? What's the formula for volume? You have done it in math. If the base area is A and the height is H, what is the volume? A times H, correct. So then you have rho times A times H. So the mass is rho times area times the height. Is that clear so far? Okay. So I'm going to use that over there. So pressure is equal to, so what is mass? I'm going to transfer this mass over there. Pressure is equal to mass times gravity over area. So mass is rho times area times h, and then you have the g there. So I brought the mass here. Can you see the mass? This is the mass. That's a mass over area. What can I do now? No. Can you see something special over there? Rho A H G. Cross out the A. You don't want the A there. A goes. So what is left now is rho H and G. This is the equation for the pressure in a fluid. This is the equation for the pressure created by a fluid. Equation for pressure created by a fluid. I can write PF if you want. Fluid pressure. The pressure created by the fluid. So what are the factors the pressure created depends on? The pressure created depends on, one, density. Next, height. What's the other one? Gravity. All right. So if I have the same beaker of water on the moon, it's definitely going to exert less pressure on the floor, right? And the other two factors are density and height. So if the density is more, if I'm going to use mercury in that same beaker, will it exert more pressure? Yes. And of course the height. The more the height, the more the pressure. So these are the only three factors affecting pressure. No, height, density, and gravity. Three factors. It does not depend on anything else. Now here is an example for you all. This is a fish tank. So that's a fish tank. That's a fish tank. And then I've got another measuring cylinder. You know what a measuring cylinder is? You've seen it in chemistry. So I've got a tall measuring cylinder and I've poured water into it like that. So this is a tall measuring cylinder on the right hand side, and this is the fish tank. Tell me, where is the pressure more? Is it at the bottom of the fish tank or the bottom of the pressure, measuring cylinder? Why? But isn't the weight of the water less? Where? On the fish tank? Why? There's a lot more water in the fish tank, so is the pressure more? What about you all at home? What's your answer?
The bottom of the cylinder.
The bottom of the cylinder, more pressure? Think of this, the cylinder has only little water. How can you say that that will offer more pressure? Look at the fish tank, it's got a lot of water.
The area is less.
The area is less. Okay. Now, I just taught you the pressure by the fluid depends on what factors? Now, did area come into play? No. Did the weight come in? No. So now tell me the answer. Is the height the same? Density is the same? Gravity is the same? So what do you think about the pressure now? It's the same pressure. Do you understand? The pressure at the bottom of the measuring cylinder and the pressure at the bottom of the fish tank are exactly the same because pressure depends on height and density and gravity. And if all of these are the same, definitely the pressure is the same. Now, even if it was a big pool, even if it's a big pool, if the water is exactly the same height as what you have in the measuring cylinder, what do you think is the pressure at the bottom of the pool? Same. So don't worry about the quantity. It is the depth of the water that matters. You understand this? Yeah. Which means what? If you go 1 meter, if you go 1 meter deep into a pond, there will be a certain pressure there, right? You go 1 meter in a big Michigan lake, it's the same pressure there. Doesn't matter how much water is in Michigan lake, right? You understand this? You're going 1 meter down, that's all matters. As long as the water is the same in the pond and the Michigan lake, it's water. Now, if you go 1 meter in seawater, then the difference will be there. Because it's denser. Because density is also one factor. So if you go 1 meter in lake and 1 meter in the sea, definitely in the sea the pressure is slightly more. Clear? Okay, don't get confused on that concept. It's very Yes. Yes. If the cylinder has salt water in it, definitely the pressure is more in the salt water tank. Make sense? So it depends on three factors. One is the height, then the density, and then the gravity. Of course, if you're on the surface of the earth, the gravity is going to be the same sort of thing, right? That's not a major issue. The major issue then becomes the height and the density. A very common misconception is this, that just because it's a lake, the pressure is more. No. You're going the same depth, then the pressure is the same thing. Okay, so you understand the pressure of fluids? Now, pressure in fluids is rho GH. Is air a fluid? Air is not a fluid. What did I say fluid is? Anything that flows. In the last class I told you. What did I say? I mean, like, I gave you the... I started the class by saying what? Anything that flows is a fluid. Liquids and gases are collectively called fluids. Where are you all? You're at home taking notes. I suppose you're taking good notes. Anything that flows is a fluid. Gases and liquids are both fluids. Air is a fluid. So right now we are at the bottom of a sea of air. We are at the bottom of a sea of air. So is air sitting on us right now? Yeah. So will air exert a pressure on us? Yeah. And that pressure is called atmospheric pressure. Atmospheric pressure is a pressure exerted by atmosphere. Atmospheric pressure is a pressure exerted by the atmosphere. So this is the earth. I'm not drawing the whole earth. That's the earth. And the atmosphere is just like that. Atmosphere is just a little layer. So what is up above the atmosphere? So this is the atmosphere. That's the atmosphere. What is above the atmosphere? Vacuum means what? Nothing.
So is the atmosphere putting pressure on the Earth?
Yes, it is. And on us. And on us too. Yeah.
Oh, why doesn't the atmosphere just kind of like fly away?
Say it again.
Why doesn't the atmosphere just fly away?
Oh, because all the atoms are held by the gravity.
Oh, because the gravity
Is pulling on all these gases. So yeah, they can't escape. So all the oxygen, nitrogen, and all those things that are around, they are all held by gravitational force. Yeah, they are all moving. Atoms are moving, but they don't have enough speed to just fly away out of the earth. Gravity is pulling it down. That's what's containing it. And what do you think is the approximate height of the atmosphere? It should be approximately 100 miles. Not more than that. Now, of course, the density is different. It's more dense at the bottom because air is something that can get squished, correct? It's not like water. Air can get squished. So there's more density here. More dense at the bottom. Less dense at the top. So it becomes lighter and lighter and lighter as it goes up. higher and higher. Make sense? So what is the pressure at the very top in vacuum? Pressure is 0. There's no pressure. Because what causes the pressure is atoms coming and hitting us, but there's no atom there. So as long as there's no atom, there's no pressure coming up. So that is vacuum, that is space. Not a single atom is going to bother you. That is why satellites are launched above in that area. Satellites are put above that only. Satellites are not placed in below 100 miles. They put it 150, 200 miles above, or 20,000 miles above. That's fine. So satellites cannot be put into an orbit in the atmosphere because the atmosphere will actually burn it. All right. So pressure above the atmosphere is 0. And as you start going down, see, look at this. Look at the example I gave you about this liquid. Where is the pressure most in that liquid? At the bottom. The deeper you go, more pressure, right? The same way here. On the very top, you start with 0 pressure. And as you go down further and further, the pressure will be higher and higher and higher and higher. And the highest pressure is down here.
Is that like when you see like stuff coming into orbit and it's like on fire kind of?
Yeah,
Is that the
that's right. Yeah, because once it enters the atmosphere, the air, like brushes past it, and it just like it produces so much heating that it just starts burning. It is friction. Just like how your leg, if somebody drags you on a carpet, you can get burnt, right? The same way. The rockets and all that, if they enter the atmosphere at a high speed, they can actually burn. So that's why before they enter the atmosphere, they have to control their speeds and all that. By using retro rockets, they control their speeds and then slowly they enter. Shuttle, the space shuttle, when they enter the atmosphere, they enter gradually. Yeah. Now, at what height planes fly normally? 7 miles. That's it. Oh, the density keeps changing. It's like at 100 miles height, you'll see atoms, one there, one there, one there, And as you go down further and further, it becomes thicker and thicker and thicker and thicker. The thickest is at the very bottom.
So why is it when you leave the atmosphere, you don't just keep burning up? Like,
Say that again?
I'm trying to make sense of this. Like, just when you're entering the atmosphere, you start to like burn up, right?
Yeah.
Burn up. But when you leave it, doesn't it like stop burning up?
No. When you leave the atmosphere, when you're shooting upwards.
Like when you're coming back down.
Oh, when you're coming back down, you don't burn until you reach the atmosphere.
Keep going.
Like meteors, for example.
Mm-hmm.
The meteors are coming from outside. They don't burn.
Yeah.
It's just a big rock that's coming in. Mm-hmm. And they just come in. As soon as it starts entering the atmosphere, that's when the burning starts.
Right. Like after you get to like past the atmosphere, like kind of in between the atmosphere and
It'll keep burning. In fact, the burning will become more and more as you get closer and closer.
I thought it was only in the atmosphere. Is it not?
Well, the atmosphere is all over. There's not a part of it in the earth. The atmosphere goes like.
Yeah, it is like it's from the ground all the way till around 100 miles.
Okay.
That little red line.
Yeah, that's the Earth is this. The red line is the Earth. Exactly. You got it? So like the Earth goes all the way like that. Okay, so understand that part of it. So what I'm trying to say is this. Since all that air is standing above our heads right now, we are exerted. So all the weight of that air is sitting on us now. Think of it. All the weight of the air of the atmosphere is sitting on us and is creating pressure on us. And that pressure is called atmospheric pressure. Now tell me, what is the atmospheric pressure at the very top, above the 100 miles? Zero. Now, the highest pressure is near the Earth's atmosphere, Earth's surface. It is like 14.7 psi. Well, it's not a constant. It changes accordingly. If you are on top of a mountain, will the pressure be more than 14.7 psi or less? It'll be less, because if you go to a mountaintop, only less air is above you then, right?
Does that mean that you would, no, I don't know. I'm gonna say, does that mean if you jump off and you fall slower than what?
No, gravity is different. Gravity is different. Gravity is different. Gravity also goes down, but not tremendously.
Yeah.
But the pressure goes down pretty well. In fact, when you take an elevator, I'll tell you this. When you take an elevator and go from the bottom floor to the 30th floor, the pressure at the 30th floor level is less than the pressure at the bottom. That's why your ears will start popping.
Is that why when you're people on like the top of the impact hit, or not Everest, or that full breathing, is off the mask, because
They can't. Yes, exactly.
dive, like the bottom of the sea, or like with everything, like,
Yeah,
the
exactly. The pressure is a big deal, actually.
The closer you get to the earth floor, it keeps getting more and more.
Exactly. Yep. You're right. So the pressure actually is a very strong thing that we need. So people who are going to run on top of a mountain, you will have less air to breathe because the density is less there. So therefore, you won't get the same oxygen that you used to get on the ground level. You understand what I'm saying? So there's a big difference. So some people actually to create better stamina and all that of running marathon, they go there and then they run and practice so that when they come down here, they'll find it easy. Because you get a lot of oxygen here, right? So yeah. So what I'm trying to say is this: as you go higher and higher, the pressure starts weaning off. It keeps on dropping. So 14.7, yes, is at the bottom here right now. Right now we are 14.7. Okay, we are slightly above the ground, but yeah, a little bit less. But if you're going to a tall building to the top, yeah, it is further less. The higher you go, the lesser the pressure. Make sense? The 14.7 psi is not a joke. 14.7 pounds every square inch. Which means what? Imagine you make if you take a tube, you take a metallic tube. Suppose you take a metallic tube like this, like an aluminum tube. You have an aluminum tube, 1 square inch. You know what I mean? It's one inch by 1 inch. And you fill it with air all the way 100 miles. How much will be the weight of that air? It'll be 14.7 pounds. How much is the weight of air that we measured here in this room? It was like 200 and something kilograms, right? In this entire room. But I'm talking about in that channel, if you put air, it'll be 14.7 pounds. That's a lot. So 14.7 pounds per square inch.
Would it be less for the top of the episode?
Huh?
Would that be less for the top of the episode?
No, here, what I'm saying is you have this tube of 100 miles thickness, 100 miles tall, and you fill it all the way with air. Of course, yeah, the density is very little on the top. But overall the weight of the overall air is going to be 14.7 pounds. So every square inch is 14.7 pounds. Every square inch. Now it may look a little small, but think of this. This paper, this printing paper that I have in my hand. The printing paper is approximately, this is around 11 inches, right? And this is around 8 inches. So you have 8 by 11, right? So how many square inches is that paper? How many square inches?
88 square inches.
88-inch square. On each square inch, how much is the force by the air? So tell me, how much is the force by the atmosphere on this paper right now? Force is pressure times area. 1,293 pounds. Think of this poor paper. This paper is now pushed by what force? 1,293 pounds. Then why is this paper not getting torn into pieces?
Because it's pushing back with the same amount of force.
Because it's pushing from the other side the same amount of force. You get it? Yeah.
What would happen if like that force was just like taken away, like the 14.7 pounds per square inch? Would you just like everything be the
It'll move. No, not float. You can see this. I'm showing a demonstration here now. People who are at home can see it also. Like I'm just holding this paper like this, right? What's the pressure? What is the force from here? 1293. What's the force from here? 1293. What is causing the force? Atoms are hitting it, right? Now what if I scoop some of those atoms and say, get away from here? What will happen? The force will be less than 1,293. So see, what I'm going to do is I'm going to push the atoms away. Watch. What happened? The paper moved towards my hand. Because as soon as I pushed the paper like that, see? As soon as I pushed the paper, the pressure on this side dropped. So the pressure on this side is pushing the paper this way. That makes a big difference. And you know, a huge amount of forces can be actually felt by this. You understand atmospheric pressure? Right? And 14.7 psi. Yeah, you know, think of this. You're driving your car. Now we'll get to these topics later on. Imagine you're driving your car and a truck just passes by on your left. Think of this. A truck just passes by on your left. What do you feel? The car will actually move towards the truck, right? Like it will sway this way. Have you felt it? Why? Because when your car was going straight, the pressure on both sides of the car are exactly the same. As soon as the truck went this way, it just disturbed those air particles on this side. So it dropped the pressure there, which means it drops the force. So the car will get an imbalance of force. There's more push from the right side, less push from the left side. So your car kind of sways. Get it? So yeah, we'll be talking about this. Now 14.7 psi in terms of pascals, it is 1.01 times 10 to the power of 5 pascals. This is the Pascal pressure, or 101,000 Pascal. This is the atmospheric pressure. Now in PSI it is 14.7. Why I said PSI is because for you to understand it, right? You understand PSI better. That's why I gave you this. Now the next concept is absolute pressure. Absolute pressure is the actual pressure. Actual pressure. So let me go back to the beaker of water. You know that the pressure created at the bottom here by the fluid alone, PF. How much is the pressure created by the fluid alone? Rho G H, correct? The fluid alone creates a pressure which is rho GH. Now what is the pressure above the fluid? What is this? What is pushing the surface of the fluid on the top? Atmospheric pressure. So on the top is pressure atmospheric. So what is the total pressure down here? What is the total pressure down here? Is pressure atmospheric plus pressure of the fluid. Did it make sense? You understand this part clearly? Yeah. Okay. So absolute pressure is a term that is used to say actual pressure. What is the real pressure? That's called absolute pressure. And that absolute pressure is the overall pressure at the bottom. The fluid creates this much pressure, but atmosphere is pushing above the fluid as well. So you have to add that also. So what is the total pressure at the bottom? P atmosphere plus PF, and this is called absolute pressure. Got it? The next thing is called gauge pressure. Gauge pressure. Have you used a pressure gauge? Yes. You have used a pressure gauge. Okay. Now here is my question for you. These are your tires. And that's where you put the air into the tires, right? So you said you have used the pressure gauge? You have. Excellent. Now, let's say you have a flat tire. Means somebody slashed your tire, cut the tire, and it's totally flat. Yeah, it's flat in the sense like somebody tore it. It's not a hole, it's torn. Okay? Let's say the tire is slashed and cut. Now you come and stick your pressure gauge here. What will it read? 0. Correct? But what is the pressure inside the tire? What is the actual pressure inside the tire? The absolute pressure. Yeah, that's right, 14.7 psi. Because there is air. It's not vacuum, right? The tire is cut, but there is air still inside. Then why is our pressure gauge not reading it? Because the gauge pressure, the gauges only read the pressure difference between the inside and outside. It cannot read. Exactly. So gauge pressure is the difference between inside and outside. So what was the outside though? 14.7 psi, right? So if the inside is 14.7 psi and outside is 14.7 psi, that is why it is reading 0. So the pressure gauge will read 0. Now let's say you put the gauge here and it reads 30. And outside is 14.7 psi. So if the gauge is reading 30, what is the actual pressure here? You're right, 44.7 psi is correct. So when you're actually putting 30 psi on your gauge, the actual pressure inside the tire is 44.7 psi. Make sense? So what is the gauge pressure? It is the difference between the inside and outside. That is why when the tires are flat, it will read 0 because inside is 14.7, outside is also 14.7. So how much more is the inside compared to the outside? That is called gauge pressure. Make sense? All right. This is the information that you need. If you understood all this clearly, you will have no issues with the quiz that you're supposed to be doing. It'll open tomorrow.
Oh, it's like a homework or like a
It's a quiz.
Is it major or
It's a major. It's a major grade.
and when's it due?
I think I'll give you 2 chances to do it. Okay?
Is it average or is it,
Oh, that's a good question.
and when's it due?
It's due. I'll take the best score. I'll take the best score. It will open tomorrow and it will stay open. I think I'll put this assignment for the next quarter. So it is due tomorrow, but the score will be actually posted for your.
Oh, it opens, you only have 1 day to do it. It opens tomorrow.
Exactly.
I didn't know if you had.
It'll open tomorrow and it will be done tomorrow. Is that clear?
I didn't know if you had.
Yes, and you said it's quarter 4.
Yeah, it will go to quarter 4. That will be your first grade to quarter 4. Any questions? Good. All right, let me stop this here.